here we want to find both maximum and minimum in a given array with n elements. First, we consider n is an even number. So we use this method. First round, we pair all the elements. Perfect pairs. All elements are paired. Then we do comparisons. Yeah. Here, I think, yeah. So all right. So then, after that, we have winners group and a losers group. In winners group, we apply n over 2 minus 1 comparison. We can find the maximum. Losers group, all right. Same number of comparisons, we find the minimum. At the end, let us calculate the total number of comparisons. Add those three numbers, we get this many comparisons. Yeah. All right. Here, before we move to the next case, the odd case. Here, let me just tell you another result, another useful result. Yeah. This solution. So this solution is optimal. Is optimal, okay? The best you can do to solve this problem. Optimal, yeah. So we can prove it, all right? Yeah. But the proof much harder, okay? So there is a proof. Very smart proof, yeah. But it is very, pretty hard. Yeah. Okay, yeah. I do not want to do the proof in class, yeah. But I can record a video to give you the proof. If you are interested, you can watch that video. Okay, yeah. But I do not want to use our class time to do it, yeah. Because we need at least half an hour to prove it. Yeah, too much time. Yeah. All right, let's move to the odd case. Odd case. For odd case, so here I want to go back to the problem-solving strategy. Problem-solving strategy. Yeah, here, typical situation. In problem-solving, many times we have multiple cases. When we have multiple cases, our strategy is we always work on the simplest case first. Yeah. Here we have two cases, even case, odd case. Before we start, first we need to determine which of the two cases is easier. Yeah, it's very easy to see even case easier. Why? Because all the elements can be paired. Okay? Yeah. No singleton. Yeah. Odd case, you need to deal with a singleton special case. Yeah. So that means you need to do a little more work. Yeah. All right. So we pick even case first. Then, so in general problem solving, after you complete your work for the easiest case, then you have a lot of experience. Okay? And you have current result. So that's the assets you have, you can use to solve the remaining cases. Yeah. Here we use we can treat as intermediate results. Okay? We can use the intermediate results to help us solve the odd case. Yeah. For odd case, only there is small difference. That singleton element, that's the small difference. Yeah. So we only need to do extra work on the special, the difference part. Yeah. All right, so let's look at how do we add a little more work on the difference part. Yeah. Yeah. So this time, what's that? Oh yeah. So this time here, you can see, right, singleton, right? Other case. So we have this element. No pairing for this element. So we take it out. Okay, all right. Yeah. So here, that strategy, problem-solving strategy, bridge the gap. There is a gap between even case and odd case. There is a gap. So the gap part, this singleton is the gap part. Yeah. So we need to, here, we need to, mainly we work on the difference part. Yeah. Right. If you can find a nice way to take care of this difference part, then you complete it. You complete the solution. That's simple. Okay. All right, so let's do it. All right. Now, in the second round, so the first round we do the comparison in all our pairs. Okay. In all our pairs, no comparison here. Yeah. No problem. Let us move to the next round. In the next round, now we need to do the grouping. Okay? Grouping. Okay? When we do the grouping, we borrow our experience from the even case. In our even case, winners group and the losers group. Let's look at the winners group first. Yeah. The winners group, this part, very easy, automatically assigned to the winners group, right? Yeah. But the difference part, the singleton. How do we assign xn? So here, let me ask you this question. Is this xn qualified for the winners group? You need to answer this question. Is xn qualified for the maximum? Tell me answer this question. Winners group means there is a chance this element could be the maximum. Do you think xn could be the maximum? Yes. If it could be the maximum, that means it is qualified for the winners group, right? Yeah? Yeah? So that's our logic, right? Yeah. All right. So now, yeah, after we check the qualification, yeah, so now we can put it in the winners group, xn. We should put it in the winners group. Then losers group, we need to answer the similar question. Is xn qualified for the minimum? Right? Yeah. Is xn qualified for the losers group? Is there a chance for xn to be the minimum? Yes. Yes. Yeah. No reason to eliminate xn for the minimum, right? No reason for it. That means we should also put xn to the losers group. That's okay, no problem. This element is qualified for both groups. See? For both groups. No violation, right? No violation. Because by the underlying understanding, yeah, this element is qualified for both maximum and minimum. So that's why it is qualified for both groups. Okay? After you see this picture, now you are ready to do the counting. Do the counting. Okay, all right. First round, this time, number of comparisons, n minus 1 over 2. Yeah? Minus 1, we take out this one, so n minus 1. It becomes an even number, n minus 1 over 2, integer. First round. Second round, in the winners group, you need to count how many, the number of elements. Find the maximum minus 1. The number of elements minus 1. Okay? This is number of elements, this number plus 1. Yeah, so here, how many elements? This number actually, we need to plus 1, then minus 1. Remember? Our formula plus 1 minus 1. So then, same number. Yeah. Same n minus 1 over 2. Same number. Plus 1, what's the plus 1? Plus 1 because xn, we need to add xn, so we plus 1. Why minus 1? Finding the maximum, the total number of elements minus 1. So we also need to minus 1. Plus 1, minus 1. Then do nothing. All right. For the minimum, the same thing. Oh, sorry. For the minimum, yeah. Same understanding. Okay? Yeah. All right. Then we can calculate the total. Add up these three numbers, 3 times parenthesis n minus 1 over 2. Yeah. So for the other case, we have this formula. Even case formula for odd case formula. So you can see here, 2 formulas are slightly different. Even case, odd case, slightly different. Okay? Yeah. So even case, remember? This is even case, okay? Even. You can see slightly different. Okay? Yeah. In this situation, when you have 2 different versions for 2 different cases, many times we want to simplify the situation. Because you need to memorize 2 different formulas, right? Yeah. You need to memorize 2 different formulas, and it's very easy to get confused. Yeah. Confused. Yeah. So in this situation, people want to simplify it. Simplify this situation. How to simplify it? Can we unify these 2 cases? Can we use one formula to cover both cases? One formula, okay? We don't want to memorize 2 formulas. We want to use one unified formula to cover both cases. Let's do that. All right, unify the 2 formulas. For the even case, this formula. For the other case, this formula. In order to use one formula to cover both cases, when n is even, that formula equals the is odd, that new formula equals the lower one. That's what we want to do. To do that, we need to compare the difference. How much is the difference between these 2 versions? There is some difference, but what's the difference part? We want to see that difference part. Okay, all right. All right, strategy. Let us compare the similarity between these 2 formulas. Similarity, similar part, so the new formula can share that similar part. But difference part, the new formula should find a nice way to take care of the difference part. All right. Let's explore the similarity between these 2 formulas. First formula, let us put it here. All right. Second formula, let's try to write it in some way. Because minus 2, look at the minus 2 here, right? Minus 2. But second formula, there's no minus 2, right? Let us try to, use the same format as the first case. So we do minus 2. If you do minus 2, you need to plus 2. Yeah. Because you cannot change the value. So when you do minus 2, you should also plus that 2 back. To keep the same value. You cannot change the value. Okay? All right. After that, yeah, so now minus 2 part the same. Okay? Yeah. That means the new formula can do the same thing in this part. But then there is a difference part. Let's look at after simplification, yeah, now the difference part. Even case, the first term, other case, the first term, they have slightly different case. All right. Next, we need to use one formula to cover both cases based on the even odd case. Okay? One formula to cover both. Yeah. In that case, yeah, in this situation, even odd, based on even odd, this situation, so here, before I introduce the new formula, first, let me show you another special property to show, to give you the idea. We need to find another useful property. Okay, all right. Both formulas, both mean number of comparisons, right? Yeah, both mean number of comparisons. The number of comparisons must be integers, right? Yeah, must be integers. All right. 3n over 2 to be integer, n should be even number, right? If n is odd number, 3n over 2 cannot be integer. Okay? All right. So here, 3n plus 1 over 2 to be integer, n must be odd, right? If n is even, 3n plus 1 over 2 cannot be integer, right? Yeah. So here you can see the reason these two formulas are different, because we want to get integers. In order to get integers, we have to do an adjustment. So you treat this plus 1 as the small adjustment in order to get an integer. Yeah. So you see the bottom reason. That's the reason. Yeah. Why you do this difference, plus 1 difference? Because we want to make it an integer. So next question. Can we get an integer without plus 1? Yeah, because this plus 1 is the difference part. Here we want to take away the difference part. When we take away the difference part, we don't want to plus 1, but we still want to get the integer value. Is there any special way to do it? Yeah. Some number is, so here, let me explain. Okay. Suppose I cross out this plus 1. Definitely the value is different, right? But after I cross out, this 3n over 2 becomes non-integer, right? It's non-integer because I remove 1/2, right? I take away 1/2 from integer. How do I recover that 1/2? In a special way. Make it integer. I want to add that 1/2 back, but I don't want to explicitly add that 1/2. Ceiling function. We take ceiling function, we round it up to integer, right? When we take ceiling function, we round it up to an integer, but we do not explicitly add that 1/2 back, right? That's the trick. We use the ceiling function. Plus 1 tells us we should round it up, right? Round it up, we use ceiling function. Round it down, we use floor function. Yeah. So based on that understanding, we here, okay, all right. Yeah. Based on that, our final form, ceiling function of 3n over 2. Yeah. Yeah. Then minus 2. So this formula covers both cases. Both cases. Here you can see, yeah. Here I use a lot of time to explain this little special case because I want to introduce one special thinking method in problem solving, how to do something special to cover the difference part. Difference part. Yeah. Yeah. The common part, yeah, we know, we have it, the common part, but there is a small difference part. So we need to do some little thing to take care of the difference part. Yeah. So that's some basic problem solving strategy. Yeah. All right, yeah. So now, after this analysis, later you only need to memorize one single formula for this problem. Okay? Yeah. Seeding function, yeah. 3n over 2, yeah. Then minus 2. Yeah. Yeah. And you also know this solution is optimal. Optimal. Yeah. So I'll give you this solution. Yeah. So optimal. Okay. Yeah. You know the meaning. Yeah. Optimal. Yeah. The proof. You know, relatively hard. Yeah. All right. Yeah. 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 I can make a video. Yeah. You know, attached to the bottom of the lecture video if you want to understand it, so you can watch that video. All right, so we complete this whole topic. Yeah. All right. Next, let's go to part B of Module 2. Part B. Now, finally, we need to do some extra, abstract part of this class, the most abstract part of this class. Growth function concept. Yeah.
This is abstract because it doesn't really, you have to make the formulas yourself.
Yes, we use abstract notations to represent some special meaning. Yeah, that's why it's very abstract. Okay? Yeah. In your understanding, you need to understand some abstract concept. Yeah. Just this module, we need to do that. And for algorithm class, you have to have this kind of abstract concepts. Yeah. All right. B.1, introduce growth function. Yeah. All right. Formula between running time and number of basic operation. We know the running time, that's the direct measure of efficiency. Yeah. But remember, this measure is not stable. So then, when we compare our algorithms, we want to use a stable measure. So that we do the counting. We use the number of basic operations, this measure, to replace running time measure. Now, two different measures. Now, the first measure is direct measure but unstable. The second measure, it's a stable measure. Yeah. Much easier to use. Yeah. So we need transition between the first measure to second measure. Yeah. What's the purpose? Yeah. Here, if you want to ask me, what's the purpose? We want to find a good way to describe the efficiencies of algorithm. That's our purpose here. Okay? We want to describe efficiency of algorithms. Okay? Yeah. When people ask you, what's the efficiency of your algorithm? Yeah. Yeah. Old times, people use performance. Yeah. But recently, people use efficiency. Yeah. Old time people, we want to study the performance of the algorithms. Yeah. Yeah. So recently, people say, we want to study the efficiencies of the algorithms. Yeah. All right. Let's look at the relationship between these two measures. We use capital T of n to represent running time function. It's a function. Yeah. N, you know the meaning. N, data size, right? The number of elements. Yeah. Number of elements in an array. Yeah. Here we call the data size. N is the data size. Yeah. All right. Then, when we count the number of basic operations. Yeah, basic operation I mentioned before. What's the basic operation? The operation that you use most frequently in your algorithms. Okay? Yeah. That contributes the most to the running time.
Generally, it's always like you found the innermost core of the algorithm.
Yes, yes. Yeah. 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 Contribute the most to the running time. Yeah. So yeah. Mainly, yeah. You do your counting on that operation. Yeah. All right. Yeah. So contribute the most. Right. Then the relationship, yeah, now to connect these two functions, we need to introduce a constant, a special constant. This little c op, little c, that is the execution time of one basic operation. One basic operation, for example, one comparison. How much CPU time you need to do one comparison, right? Yeah. So there is a number. Here we use this little c for that number. Comparison. Or multiplication. If your basic operation is multiplication, what's the CPU time to do one multiplication? That is little c. Yeah. All right. Then we can look at the approximate formula. Here, when we do analysis, we use approximation. All right. This approximation approach, capital T function, T of n, approximately equal to little c constant times capital N, capital C of n. Yeah. Yeah. Okay? Yeah. One basic operation, you need a C op, okay, little c op time, but you have total capital C of n, basic operation, you do direct multiplication. Okay? But that's approximation. Yeah. Close. Yeah. All right? Yeah. Based on this relationship, now we want to see. So we want to go back to our original goal. We want to study the efficiencies of all the algorithms here. We do not talk about one particular algorithm. We talk about general algorithms. All possible algorithms for all computing problems. Okay? Yeah. When you talk about that, very messy, right? Yeah. So, very messy. So many cases, too messy. If the data is very messy, what should we do based on our experience? Yeah. So far, we have a lot of experience. When we encounter messy data, unorganized data, what should we do?
By the way, can there be like a notation, like a symbol that denotes the basic operation instead of having to write out the whole phrase basic operation, like word for word basic operation. Instead of that, we can have a symbol that denotes that it's the basic operation.
Yeah. Symbol denote basic operation. So here we do not use symbol for the So here we count the basic operations. Yeah. So here we do not go to the details of the basic operations. Yeah. All right, continue. Want to say something, Annis? Back to the problem. When we encounter some unorganized data, very messy, what should we do? Sort? He said sort. Yeah. You get a little sense. Yeah. Yeah. Because you want to organize data. Yeah. Sorting. So that's the get the data organized. All right. Any other answers? We did before. We did it before. Find common property. Not that. Recall our chessboard question. Chessboard. What did we do in the chessboard example? Chessboard, the data relatively messy, right? The number of squares, covering many different sizes. Yeah. One word, one keyword, yeah. Special keyword, yeah. Characterization. Characterization, okay? We organize the data based on different categories. And we want to choose appropriate categories to organize our data. Yeah. Size 1 category, size 2 category, one by one size 1 by 1 category, size 2 by 2 category, things like that, right? Yeah. Yeah. But here we do not have that kind of obvious characterization. Here we also want to do characterization, okay? Because all the algorithms for all the computing problems, too hard to control, too hard to manage, okay? So here we want to choose appropriate categories, put all those algorithms in different categories. How about that? Yeah. Here the question is how to choose appropriate categories. All right, so we need to further study this formula. Try to give us some information on the characterization of the algorithms. Okay, all right, yeah. So let's continue. All right. Here, these two functions are proportional, right? Yeah, they're proportional. Yeah, little c constant, we know. Yeah, multiplication, that's the proportional relationship. All right. So if these two functions are proportional, yeah, based on, you need some math experience here. Yeah. Yeah. Because here, this little c constant, still, for different machine, for different computer hardware, that little c is different, right? Sometimes this number, when you move to a different machine, you have a different little c number. Yeah. That's quite annoying. That is not very convenient. Can we find a way to get rid of this little c? Yeah. We don't want to make this little c as some impact factor. Because that increases the difficulty of our discussion. We want to find a friendly way to get rid of this little c. Some friendly way. Yeah. Remember, we want to do characterization. When we design our categories, we don't want to make this little c as an impact factor. That's reasonable, right? Yeah. Our characterization should be very neat, okay? Very simple, very neat. Yeah. So not, too complicated. Yeah. This little c, that little c, you have 100 little c. We don't want to have those things, right? So we want to make it extremely simple. Yeah. So we want to find a way, find a nice story. So here, I'll go back to our human intelligence. Here, what we are doing, we use our human intelligence, not a machine, so-called intelligence. Okay? Our human intelligence, what's the strength of typical human intelligence? What's the main strength of human intelligence? So versus AI. Human intelligence. Yeah. I mentioned before, we have understanding. We have comprehension, right? Machine cannot do it, right? AI has no understanding, okay? AI has no comprehension, okay? So our human intelligence, we use our understanding. We can make stories. We can make reasonable stories. Machine cannot do it. What AI can do, what typically AI can do, AI based on two big block of foundations. 2 blocks of foundations. Yeah, what's that? The first one, statistics. It can access large amount of data, then do statistics to extract useful information from large amount of data. That's the strength of AI. First one. Much stronger than human. For us, it's very hard to do statistics on large amount of data. So AI can do it. That's the first one. Second strength, AI, logic reasoning. Okay? Because following the given rules, do logical reasoning, AI needs to use logic rules. Based on logical rules, AI can follow the rules, doing logical reasoning. Okay? These 2 things, that's the strength of AI. But AI cannot understand. What's the meaning of this concept? No. AI knows nothing. Okay? AI generates output, just output. Okay? Yeah. We human, we need to control. If the output is not right, we need to change the algorithm to make it right. Okay? But AI generate the output to satisfy our needs. Okay? If we human, we feel the output is not right, then we need to change the parameters. We need to change the functions. We need to change the systems to make it right. Okay? But AI does not know anything. I just based on the algorithms, the data, I just produce the output, whatever it is. Okay? Yeah. So here, the reason I say this is we need to know our strength understanding. AI can never do understanding. Okay? AI can never do understanding. Yeah. So from this you can see AI can never replace us. If you go to the understanding level, if you do things without understanding, AI can replace you easily, right? Yeah, because that's the strength of AI. That's why I emphasize when we work on the problem, we really need to use our strength, understanding. Yeah. With understanding, we can create new things. AI cannot create new things. Yeah. AI only produce based on the algorithms. Okay? Yeah. So now, so for this class, understanding, you will see, very important. Yeah. All right, so here, in order to get rid of that little c, yeah, we want to ignore unnecessary details. Now, don't add too much details here. Okay? Don't add any details. Yeah. We try to reduce the details here. Yeah. not adding details, all right? Yeah. All right, so now we try to ignore that little c. Not ignore. We try to find a nice way to take it out. Yeah, take it away. Yeah, all right. All right. Another thing, yeah. Remember, in a function, there are many terms. Some terms are major terms. Some terms are minor terms. Here, another way to simplify a function is ignore some minor terms. Yeah. All right. Yeah. All right. Then let's look at what is the nice way to eliminate little c constant. When we take a ratio, here, we know when two functions are proportional, yeah, when we take a ratio, we cancel out little c. Yeah. Yeah. So here you can see, you take the ratio, you double the problem size, t of 2n, double the size. Yeah. T of 2n over t of n approximately equal to c of 2n over c of n. Yeah. So then you need to understand what's the meaning of this ratio. What's the meaning? C of 2n over c of n. What is the meaning of this, the ratio of these two function values? Yeah. The meaning. Can you see some increasing information? You double the size, your function should be larger, right? Remember, C function represents counting number, right? You count the number of basic operations. When the data size is larger, is your counting number should be larger, right? When you work on the larger problem sizes, your counting number should be larger, right? Naturally, it should be larger. Yeah. So here, C of 2n is a larger number. C of n, relatively smaller number. You take the ratio, larger number over smaller number, but the larger number corresponds to the double of the original data size. Does this ratio give some increasing rate? Some kind of increasing rate, right? Yeah. Here. We use this ratio form on two different functions, on both t function and the c function. Here, this formula tells us these two functions have the similar increasing rate. See? Yeah. These two closely related functions. They are two closely related functions. Yeah. They have the similar increasing rate. Yeah. If we define increasing rate as the ratio of this form, yeah, they have the same increasing rate. How about that? In this way, we do not need to use little c constant. We do not need to use little c constant. Okay? All right. Yeah. All right. So here you can see, yeah, when we do the characterization, we can find a way without using little c constant. Yeah. All right. Yeah. Next, this time we need to talk about a new concept, a growth function concept. Yeah. All right. Yeah. Yeah. In order to show you the necessity of this concept, I need to go back to look at the first round approximation, the major term. We use the major term to approximate the original function. Original function, relatively complicated. Okay? So we want to simplify it. The first round simplification. we make a first round simplification. Okay? Make it simpler. How to make it simpler? We use the major term. Yeah, what's the major term? Yeah. Yeah. Dominant term. Yeah. I talk about this dominant term concept in our linear search problem. Linear search, I introduced this term. Yeah. Here, let me recall. Yeah. Recall this dominant term concept. Yeah. So let's look at the selection sort. In the selection sort, all right, we know the total number of comparisons. This is for the worst case. This is the worst case. Okay. Worst case, the total number of comparisons. Yeah. Now, we want to simplify it. Yeah. Simplify this counting number. All right. We keep the major term. We keep the dominant term. And we throw away the minor terms. All the minor terms we throw away. Yeah. All right. So here, after the expansion, there are two terms. The first term, second term. The first term is larger than the second term. So we treat the first term as the major term, second term as the minor term. Yeah. Now, we take a first round approximation. Can we throw away the minor term? Throw away. Yeah. Minor term. Yeah. All right? Yeah. Is it big loss if we throw away the minor term? Is it some big loss? Yeah. Yeah. All right. Yeah. To understand, it's not a big loss. You're correct. It's not a big loss. Yeah. But later we need to do more understanding. Why it's not a big loss? Yeah. We need to do more understanding on that. Yeah. Yeah. It's true, not big loss. Yeah. We'll throw away. Okay. Yeah. All right. So, and this circle term, that's our dominant term. Okay? So we call it dominant. So this term dominates all other terms. Yeah. How dominate? Yeah. So you may want to ask how dominant it is. Yeah. We can do the calculation. Okay? We can do calculation later. How much it dominates other terms. Yeah. All right. Yeah. Here, let's do some simple calculation. Yeah. This time we need to use some calculus. Calculus. Take the limit. Let's calculate the limit of these two functions. Numerator, dominant term, major term function. Denominator, function. Limit. Yeah. Recall a little bit. Calculus. Calc 1, limit. Okay? All right. When we calculate limit, the constant cross out. 1/2 constant cross out. And cancel out. So after simplification, we just calculate the limit of n when n goes to infinity. What's that number? What's that limit? N goes to infinity. And we want to calculate the limit of n. What's that? Infinity. Infinity, right? Yeah. It's not a specific number. Not specific. Infinity is not a number. Okay? Infinity is not a valid number. But it's some phenomenon. Okay? Yeah. So we need to use this special phenomenon here. All right? So limit. When the ratio is infinity, where n goes to infinity, are you convinced the numerator term dominates denominator term? Yeah. Because comparing between numerator and denominator is only a tiny portion of the numerator, right? Very tiny. So this time, after you see the limit, this time you feel very comfortable to ignore the denominator part, right? Yeah? Yeah. So that's the meaning of the dominance. How strong is the dominance here? Right? So strong. This infinity tells you the dominance is very strong. Okay? All right. Yeah. That's the first round. So we only take the dominant term for the first round approximation. Then the second round, okay? This 1/2 is a constant, right? Constant. All right. Remember, what is our goal? What we are doing? We do the simplification here. We do the approximation here. What is our original goal? We need to keep in our mind our original goal. That one keyword, one special keyword, characterization. All right? We do characterization. Okay? Do we have freedom to choose our categories? Do we have the freedom to choose our categories? Yeah, we have freedoms. Yeah. We, as humans, we have freedom to choose. Yeah, so always keep in mind, yeah, because we're human. We're not machines. Yeah, we're not machines. So we have freedom to choose a lot of things. We have freedoms. Okay? Yeah. The machines, they have to follow instructions given by us. Okay? So that's different. Yeah. So now we use our freedom to do another round simplification. This round, we cross out this 1/2 leading constant to do further simplification. Okay? So 1/2 times n squared. All right? Let us keep the most important part. Okay? We just take n squared part. We do not keep the leading coefficient. 1/2 we call the leading coefficient. We do not keep it. We take n squared part. Yeah. Why you can do that? Remember, we want to define categories, right? When we define categories, we put this function in the category represented by n squared. How about that? N squared, this function, we use it to form one category. How about that? That 1/2 leading coefficient, 1/2 times n squared, although that 1/2 n squared is different from n squared, but can we put 1/2 n squared in the same category of n squared? Same category. Yeah. We can, because we have freedom, right? We use our freedom. Okay? Yeah. Yeah. Try to get an idea. Yeah. Because we as humans, we have a lot of freedom. Precious freedom. So we don't waste our freedom. Okay? Yeah. So now it's the time to use our freedom. All right? To use the freedom, put not just 1/2 cn squared. We put any cn squared in the same category of n squared. How about that? Okay? So the category, each category, we need a representation. We need a representative, right? So that n squared is the representative of this category. Okay? We need a representative. All other functions in the same category, some c constant. This c cannot be 0. Okay? This c, actually it's a positive number. Okay? C is a positive number. Any positive number times n squared, we put it in the same category of n squared. How about that? Okay? This is what I mean, abstraction. I said, so this part, very abstract. So that's the meaning. What's the abstraction is? We do a lot of mental work, right? With this kind of abstraction. Yeah. All right. Yeah. So, I still have some time. Yeah. So let's continue. Yeah. Now we are ready to define the concept, the growth function concept. What is the growth function? So this function that we use as a representative of the category, this function, we call it a growth function. Yeah. Yeah. Because this function is important, right? Yeah. So it's a representative of the whole category. So we treat this function, yeah, this object, let's say this object is important. So we want to give it a formal term, okay? Yeah. Terminology, yeah. Formal term. So we call it growth function. Okay? So now you know the meaning of growth function. Yeah. All right. Yeah. So that's the definition of growth function. B.2, now after you understand the meaning of growth function, now we want to compare two growth functions. Do comparisons. Yeah. Yeah. So let's complete this comparison. Yeah, so we complete, today's class. Yeah. Let me do this. Compare two growth functions. Yeah. Here. Two growth functions correspond to two different algorithms, right? Yeah. Yeah. Because growth functions come from their corresponding algorithms. First, we need to go back to the original algorithms. Here, we go back to our problem 6, element uniqueness problem. Remember, we have two methods. We use two different methods to solve the element uniqueness problem. Here, let me give you the result.
What was that, those final notes that you made in the previous slide about the dominant term? Can I just take one more look at it, 5 more seconds? The previous slide.
Yeah, all right. Yeah. Here. All right, yeah. Yeah. All right. So here, that's the worst case. Here I use W, the worst case version. Yeah. First method, C function. Second method, C2 function. C1 function, C2 function. All right? Yeah. Now, let's take growth function based on our understanding from the previous slide to get their corresponding two growth functions. Yeah. All right. The first one, yeah, we did it. So n squared. Second one, the growth function, n log n. Okay? Yeah. Here the log, I didn't write the base. Yeah. Because in our computer science, if no base, the default base is 2. Okay? Computer science, we like to use the binary representation, right? So the base is 2. Default base is 2. Yeah. All right. Then we use the ratio to compare two growth functions. Ratio and limit. Yeah. We did one before. Now we do it again. Yeah. Do it again. Take the ratio, then calculate the limit. Yeah. All right, let's calculate this limit. After simplification, cancel out 1n. Yeah. This time, n over log n. How to calculate? How to see this limit? How to see this limit? Yeah, yeah. Here, there are some way, two different ways to see this limit. Yeah. All right. Yeah. So, or here for the calculation, we can use the general log base a. Yeah. General log base a, but we need a greater than 1. Yeah. A greater than 1, because if we use a greater than 1, we can get a positive function. If a less than 1, we get a negative function. We don't want to use negative function. Okay, so we assume a is greater than 1. Yeah. All right. And this limit is infinity. Can you see it? Yeah. This limit n over log n. When n goes to infinity, this limit is infinity. How to see it? The limit is infinity. Yeah. All right. Let me see how much time I have. Yeah, not much time. Yeah, but I will move the detail next time. But here I just talk about the method 1. Yeah. This method 1. In order to see it better, we may like to do variable substitution. So to change its form, after we change the form, we use a different view to look at the same thing, different view. Or we see the same thing, the limit of this ratio from different point of view. All right, let's introduce a new variable. This is u equals log base a of n. Because the log function, relatively complicated, right? Log function, relatively complicated. So we want to replace some complicated representation, log function, by a simple variable u. In this way, log function is gone. Log function is gone, okay? All right. So then, based on the definition of logarithm, we have n equals exponential function, a to the u, exponential function. Then, our limit, after the variable substitution, our limit becomes the limit when u goes to infinity, the ratio, exponential function, a to the u over u. We change the form. Okay? We change the form of this limit. After we change the form, we have new interpretation, right? Yeah. So this is the typical, transformation. We change the form of original object, same object. We do not change the content of the object. Still same content, but we change the outside form. After we change the form, then we have different comprehension, right? We have different comprehension. The new comprehension is the ratio of two functions, exponential function over polynomial function. Denominator is a simple polynomial function, special simple polynomial function, but the numerator is exponential function. Do you have the real world experience that an exponential function dominates any polynomial function? Do you have that kind of experience? We know exponential function increases much faster than any polynomial function. So we say dominates, exponential, increasing. Something people talk about, something increases very fast, they use the exponential rate increasing. That means very fast, right? So you connect to the real world experience. So now I can understand that ratio is infinity. All right, next time I go to the details. Here I just give you some outside understanding, okay? Not internal understanding, outside understanding.